3 lessons of machinery for producing samples. Here is what they are for. This is a quarter circle inside a unit square. Throw darts uniformly at the square and count what fraction of them land inside the curve. That fraction is the ratio of the two areas. Pi over 4. Multiply by 4, and the darts have computed pi. Notice what did not happen. No antiderivative. No calculus of any kind. We threw darts, and we counted. The general statement is short. The average of a function over your samples estimates its expectation. 1 over n times the sum of h of xi converges to e of h of x. That is simply the law of large numbers from lesson 44. And every integral is an expectation in disguise. To integrate h from a to b, sample u uniformly on that interval. The integral equals b minus a times the expected value of h of u, so estimate it by b minus a times the sample average. Geometrically, you are replacing the area under the curve with a rectangle of the same width, whose height is the average height of the curve. The samples estimate that average height, and the estimator is unbiased. Its expected value is the integral exactly for every n. How wrong is it? The central limit theorem, lesson 45, answers precisely. The estimator is approximately normal, centered on the true value, with standard deviation sigma over root n. And sigma can be estimated from the very same samples. So every Monte Carlo run reports its own error bar for free. Watch the running estimate. The band around it is plus or minus 2 standard errors, and it narrows like 1 over root n. The estimate wanders inside the band and settles. 1 over root n is slow. To cut the error by a factor of 10, you need 100 times as many samples. On a smooth one-dimensional function, ordinary numerical integration will beat this without effort. So why does anyone use it? Because of what is missing from that error formula. There is no d in it. 1 over root n holds in one dimension and in 1,000, and sigma does not care about the dimension either. Grid methods care enormously. Put just 10 points along each axis, and you need 10 to the d points in total. In 10 dimensions, that is 10 billion evaluations. In 20 dimensions, there is not enough computing time in the universe. This is the curse of dimensionality. Monte Carlo simply ignores it. 10,000 samples give roughly 1% error, whether the problem has 1 dimension or 50. That is why Bayesian posteriors, statistical physics, and quantitative finance are all computed this way, not because the method is accurate, but because it is the only one that survives. Monte Carlo integration. Write the integral as an expectation, sample, and average. The law of large numbers says it converges. The central limit theorem says the error is sigma over root n, and hands you the error bar. The rate is slow, but it is completely indifferent to dimension, which is exactly why it is the default for high-dimensional problems. The one thing you can still control is sigma. Choose what you sample from more cleverly, and the same number of samples buys a far better answer. That is important sampling, and it closes the course.